Imagine we have a source of water. That water flows in this direction, and two tap valves that when you put pressure on them, then water could flow. And well, obviously, if you don't do that, then the valve wouldn't be open and therefore water wouldn't flow. So the way that they are connected to one another, if you look, it is obvious that if both of the switches or valves are open, only then water would flow in here. If any one of them is closed, obviously that would block the water, so it wouldn't have water here. So we could show this by 0 and 1 or on or off and say if any one of the valves is off, that we show with 0, then we wouldn't have the flow of water. If both of the valves are open, then we would have the flow of water. As I said, well, we could say that the flow of water having current in the output would be shown as 1, and obviously the switches being on is also shown by 1 as the inputs. So we could abstract this as a circuit that has two inputs, which are the valves, and the output, which would be having the current, the water current, the flow of water. And obviously this would represent what we refer to as the truth table of this abstraction. Now let me show you an equivalent thing in the electrical circuits or electric circuits. Imagine that we have a battery acting as the source, like in the water example. And now we have one switch here and another one here. Obviously, we would have the switch number 1 and 2. So actually, let me show it like here that you could know it's a switch that we could close them or not. So in this case, and also I want to actually show something here as a light bulb or a lamp, maybe something like this. So the thing is that this odd shape that it is representing a lamp or a light bulb, we would have current through it and it would be on if both switches are on. So it means that this lamp would be on and we would have current through it if both of the switches of S1 and S2 are on. Otherwise, if any one of the switches is off, then you wouldn't have flow of current. So we say that if we have 0, 0 or both switches are off or any one of the switches is off, then the output would be 0. We wouldn't have any current in the output. If both of the switches are on, then we would have a current in the output and therefore the lamp or the light bulb would be on. So again, another abstraction, right? Just like the example in the water example, in here is the electric circuit example. So we abstract this circuit and we say such a circuit, we call it as an AND gate. And like we show it like here, and we say any circuit that we could say would have, well, two or more outputs, and one output, and the output would be 1, whatever we represent as 1. When all the inputs are 1, then we say that gate is an AND gate. Now, before you say, I'm pretty sure you might have seen such gates and why we are talking about them before, but I will talk about them in a moment, that why would we want to create such a thing. So now let me give you another example, this time using the transistors, what we've been creating since the beginning of the course, to create just an electronically controllable switch. So let's say that Well, we talked before that we have two kinds of transistors or MOSFET, as NMOS and PMOS. But as a brief overview, as NMOS would be on if we apply one or high voltage at the gate, and in that mode, the transistor would act as a short circuit or a resistor. And if it is a PMOS, and if we have zero, obviously it would act as an open circuit. And if it is a PMOS, then the opposite of this would happen. That if we apply a zero on the gate, the transistor would be on and would act as a short circuit, and obviously one would make it off. So if you notice, we are giving our inputs of A and B in these wires, and the out is taken from this wire. So by looking at it, it is obvious that A is being given to one PMOS and one NMOS, and so is the B. B is also given to one PMOS and one NMOS, and we know that NMOS and PMOS would get turned on in the opposite of one another. Actually, let me just show you the logic in here to see what would happen. Let's imagine that we give A and B both zeros. Well, if we have 0 on A, we would have 0 here and 0 here. And for B, we have 0 here, 0 here. The PMOSes would be on. So they would act as short circuit, just like this. The NMOSes would be off. So they would act like two switches who are open. We are getting our wires from the out, which obviously is here. We could say this is one transistor. Actually, let me use another color. So this is M1, which is on. This is M2, which also it is on, so it is short circuit. We are getting our output from this wire, and these two would obviously be M3 and M4. And if you notice, the out is connected directly to the high voltage or VDD that we call it 1. So 0, 0 would give the output as 1. What about others? Well, it is obvious that even if one of the A and B were 0, if even one of them were 0, just let's imagine that we actually had one A equal to 0. If A was 0, then the PMOS would be on, and therefore out would be connected to the battery directly. Obviously, because any one of the NMOSes is off, they would be open circuit, and therefore the connection of out with the ground would be disabled, and out would be connected to the battery voltage from either M1 or M2, depending on whether or not A or B is on. So this is saying that by having any one of the A or B switches, A or B inputs being 0, we would have the out as 1. You see, just work out the logic. Give B as an example 0, only that 0. And you would see that it would cause this PMOS to be connected directly to the out. And obviously it is connected to the M4 gate, which would be off, and therefore it would have an open circuit here. The only time that out is connected to the ground is when both of the inputs are actually equal to 1. Let me just wipe some of these things out. Too much. So let's just say that this time we would have both equal to 1. Also, let me change my color so you could better see what we are doing. So let's say, well, obviously all of them would be 1 if we give these two inputs equal to 1. So this time the PMOSes M1 and M2 would be open circuit. So this would be M1, and obviously this would be M2, and you see they are disconnected from the battery. But M3 and M4 are connected because they have 1 on their gate. So they are connected. I could show this like this, that this would be M3 open circuit and this would be M4. They are the out wire is connected directly to the ground. So we would have 0 since it is directly connected to the ground. So we say when we have both ones, we would have 0 on the output. Now what we do is that we say we have created a circuit, a logical gate, or logic gate actually, that we could abstract it. How do we make the abstraction? How do we model it? Just remember, we've been just modeling things since the beginning of the course. So we say we model this by drawing a rectangle in this form. So using this rectangle, it is obvious that we have one input and two inputs and one output. So we have one rectangle, we have one input, we call it A, another input called B, and one output that we call it out. And the behavior of this that we call it a gate is based on this truth table. We say the output is always equal to 1 unless all inputs are equal to 1. So the output is always 1 if any one of the inputs is 0. The only time that the out would go to 0 is when all the inputs would go to high or 1. And we call this a NAND gate. Now, what is special about this NAND gate is that anything in the computer world could be achieved, could be accomplished or created in the computer world, in the logic world, using this NAND gate. This is called a universal NAND gate, or a universal gate. In fact, I created a complete course called Creating a Computer Using Transistors and Logic Gates. Let me go to the preview in here so you would see. In fact, until this comes up, or some this internet doesn't work here, notice, actually, as I said, I've created so many lectures from before that how to create different things, because what is a computer? Actually, a computer would be the combination of memory and processors and other things, but actually I want this to come up to explain something for you. So creating a computer using transistors and logic gates, this is just another course, and if you pay attention, we start by defining a computer. In fact, somehow we start from the end of this course. We introduce the concept of a NAND gate and we say how we create a complete computer using this universal NAND gate. So we start to introduce the concept of a computer that is the combination of memory, processor, and input-output devices. Then we say, okay, how do we create this? What is the definition of memory? And in fact, we create a memory using simple transistors, and then we introduce what is the processor. It has several sections like registers and bus and ALU, and we create all of those things using the transistor. Even we go further and we create graphic card and monitor and other things. So some of them, in fact, I wanted to show you some of the things that I think I created actually in this lecture, or maybe in another one. Let me see if I could find it in here, I think. So in the course that you see, several circuits were created. The logic would work out only based on the switch transistor, which means actually you could even create such a thing using the water switches. That's why you might see YouTube videos or other courses which talk about how to create a computer using water switches, because any switch could work. If you could create a NAND gate using that switch, from then on you could make an abstraction and create everything from then. So we created, even though in this course that I'm talking about, we actually work everything using the pure transistors. You see, this is representing a 1-bit memory that it is controlled by an S bit. The I would go on the output, and the out would remember the input if S is equal to 0. And S is one of the wires defined in here. You see, we have S, I, and we have out. We first work out the logic depending on the NMOS and PMOS transistors, and then we make the abstractions. And then we go further and create an 8-bit register, and then we make another abstraction. We say a register with 8 inputs and 8 outputs, and 1 control bit that controls whether we could write to the memory cell or read from it. And then we go further and further and further and create All the other things, create decoders, create multiplexers. These are all the required things to create a computer. In fact, we go so much until we create a computer. So I want to show you its last lecture in which we actually create a computer and it works. That we write a program in it, a program that we defined for our computer. You see, right now, you don't know what it means, a program. It might be some abstraction for you that people say, I don't know, C programming language. But in this case, because we started from atoms, you would understand what is the definition of programming, because we defined programming for our computer. So let me just show you the last lecture of the course that I'm talking about. See, it's actually here. Let me stop it. As you see, these, all of them might right now seem like some abstractions, some models, some just rectangles, but every one of these things have been created. We have created them using transistors, and then we teach it some instructions using those transistors still, and then we program it to do something. In fact, I think the program here that we would execute, you see this 2132A in our memory that we also created, all of them would have a specific definition for the computer that we created, that we taught them. We taught our computer what is that. If you see something like A0, which A0 is actually a representation of zeros and ones, what I want you to do. In fact, it would be some loop instructions and something like that. So that would be the, you see, the goal of our lecture, that, or the course that we created in here, was from nature to processors to computers, meaning that we created a switch from the nature, from atoms, up until we create a transistor. From then on, we could create a computer using transistors, because creating a NAND gate, meaning that you could create a computer as well. And this was the goal of this course, that we create something short and intuitive for you that could make a difference. If I had such a thing a couple of years before, maybe it would have made a bigger difference for me. So everything is just a form of abstraction to maybe save some time for you. But this was the roadmap, that you take this course, you will build up some intuition from natures to processors to computers. Then you take this other course of mine that I'm talking about, that creating a computer using transistor and logic gates. And there are other courses actually that cover this content. So you could create those courses as well, these similar topics. Just pay attention that it starts exactly from transistors, because that is where we left off, since we started from electrons and atoms, so that we leave no abstraction behind. And from then on, if you still want to keep going, I created another course called the architecture of the first computer. You see, there is a huge difference between creating a computer on your own or analyzing the first computer. The first computer, the IBM PC 5150, or arguably the first PC, is much more complicated than any computer that you could create on your own. I promise you, I couldn't believe my eyes when the first time I saw the motherboard of this IBM PC 5150. It was much more complicated, a huge amount of uh, extra chips and also extra things. It is one operating system is actually put inside a RAM, a read-only memory on the motherboard of the IBM PC 5150 called BIOS. BIOS is in fact an operating system. I analyzed the source code and I would create a course most likely about why it is actually an operating system. So it does actually two things. I don't want to get into all of those things, but I would teach you that if you want, I guess, from the basic instructions, instruction by instruction. So you see, this course, I don't think there has ever been any course like the architecture of the first computer, which is a hard course really to take. That it is really tough to finish the architecture of the first computer, IBM PC 5150. But I just wanted to tell you the roadmap that if you want to be a hardware engineer or I guess expert in architecture, uh, what you should go to start from the nature and go until you could write codes for yourself or for any computer. So that's about it, I guess.